www.nanohub.org. You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Okay, so let's get started. Today we'll be talking about MOSFET current voltage characteristics and some advanced topic of it. This is lecture 36 of solid state devices. And today we'll be talking about the DC characteristics of MOSFET. As you realize, this is IV characteristics or current voltage characteristics. I will quickly review the square law or simplified bulk charge theory that we had been talking about. Now, this is called a square law because the current increases with the gate voltage as a square of Vg minus V threshold squared. So, as you, let's say you have one voltage of 1 volt overdrive, they call it overdrive, Vg minus Vth. If you have 1 volt versus if you have 2 volts overdrive, then the current would increase 4 times. 3 volt overdrive, 9 times current will increase. That's why it's called a square law. So we'll quickly review that to see why for last 20 years people haven't really seen square law being experimentally correct or experimentally observable. So this is a very simple theory for that. We'll talk about velocity saturation as being one of the reasons, and then we'll make some comments about very small transistors and the additional physics that happens here, not captured by the square law. I mean, not even captured by many semi-classical or more advanced models. So we'll talk about that a little bit. Now, if you remember that if we operate a transistor, a MOSFET, with a certain drain bias, Vd greater than 0, and a fixed gate bias, then we realize that close to the source region, which is marked at 0, let's say, close to the source region, there's a lot of inversion because essentially the full inversion occurs there and the effect of drain bias is not as significant. So you have a lot of charge there in the beginning of the channel. As you go down in the channel, along from source to drain, the charge gradually decreases. The amount of charge gradually decreases because you do not have as much inversion because of the drain bias, effect of the drain bias. As a result, in order to keep the current continuous, you realize that the velocity of each of the section, electron velocity in each of the section, average velocity, must increase, right? That is the only way current can remain constant. And the only way the velocity might increase is if you allow a larger electric field. If you allow a larger electric field in that region, in the ith section, let's say, so therefore the velocity V, shown here in red, is given by mu times the electric field E, and larger the electric field, larger the velocity, so that it can compensate the reduction in the charge and keep the current continuous. So that was an assumption we made. And using that assumption, we were able to sum up over the channel, require that in each section, without recombination, current must be continuous. So we pulled it out as something called the JD, and since we are summing over the dy, each small section from the beginning to the end of the channel, we call that the channel length, and we integrated it out and got this very simple formula. Now that's fine, except you realize that there is something wrong here, or at least potentially that could be wrong here. Assume, like in a modern transistor, you apply 1 volt in the drain. And let's say you have 20 nanometer source to drain separation, channel length. That would be a typical latest Pentium type transistors. In that case, the electric field you will have will be huge. It will be huge, very large electric field, much larger than the saturation velocity we talked about before. Do you remember that at some point, if you push the electric field too much, the velocity doesn't increase anymore. It's begin to saturate. So therefore, that physics of it is not shown in here. Here it says, put on an electric field, the velocity will always keep rising linearly. That is the first assumption in the top line, where the rate v, velocity, has been replaced by mu times electric field E directly. That is not generally true, and that is something we need to fix in order to make sure that our expressions are correct. Now, you remember that this is essentially the IV characteristics before we go on, and the square law simply says that at the current essentially peaks at the saturation velocity, and the saturation velocity, we took the derivative last time, remember, this is like a parabola that comes up and down, and then at the peak point we said the theory is valid only up to that point. We calculated by taking derivative of the current, got the saturation drain voltage, and from that drain voltage, once we inserted that in the full current expression, we got this square law. So that's something you know. What I'm trying to tell you now is that if you went in and lab and made a measurement of a MOSFET characteristics, plotted in this way, you will never find it that it goes as Vg minus Vt squared. And that's because of that wrong assumption that velocity is directly proportional to the electric field, no matter the magnitude of the electric field. That's wrong, and that's what we need to correct. So let me explain how this saturation velocity is accounted for in the MOSFET current voltage characteristics. First of all, these are very simple, so there's no reason we shouldn't be able to follow it very easily. So the main problem is this, that if I were to look at the velocity of the electrons as a function of electric field, you remember that in MOSFET, in silicon, or even gallium arsenide in other materials, by the time you sort of exceed 10 kilovolts per centimeter, at that point, the velocity field characteristics rolls over. Beyond that point, you may have, let's say, 10 megavolts per centimeter. But in that case, the velocity cannot increase anymore. So you have the velocity saturates to a particular value. Why does it do so? Because at very high field, the scattering is such. This is chapter 6 in the first part of the thesis, or first part of the course. So if you remember. So the reason why it happens is because at very high field, the scattering, backscattering of electrons is exactly proportional to the number of electrons that is coming in. So it immediately begins to have two streams going against each other. If you push this one more, the other one goes back up also, and the difference remains more or less constant. And that's why the velocity saturates. And an expression for the saturation velocity is given by this particular formula with electric field. Now, do you see that this formula might work? How this formula might work? One is if the electric field is small, E is small, so you can see in the denominator the E plus divided by EC. EC is the critical field, this 10 kilovolts per centimeter. That's the centimeter per second. That, I'm sorry, 10 kilovolt per centimeter. That's EC. So if the field is lower than that, then the second term on the denominator will be 0. And then the velocity will be just mu times c. The minus sign is because these are electrons. In the direction of the electric field will be, the electrons will be going opposite to the direction of the electric field. No problem. So now if the field is very large, then what would happen? Then the denominator, the second term in the denominator, that will be the dominant one. And the square root and the square will cancel each other, and you can see that the electric field will cancel top and bottom, and the EC will go up. So EC is a number, so the velocity will saturate at mu times EC. So that's why this actually sort of describes the saturation characteristics of this velocity field current. Now there are various forms that people use. Sometimes people use directly under the square root, especially for the holes. And sometimes they will use, instead of the square and the square root in the denominator, they'll just use it proportional to this. Regardless, that simply makes the transition region slightly different. Other than that, you can see both expressions in the low field and the high field regime will be exactly the same. In between, they might be slightly different. Now, we'd like to then use that information and rederive the current voltage characteristic. Let's see how it's done. Very simple, you'll see. So again, we go exactly the same way we did before. Take each segment, 1, 2, 3, 4 here, for example. I have divided it into 4 segments. Let's say it's 1000 angstrom. I have divided it into 250 angstroms, 4 segments. And again, I have written exactly the same expression as before. Q, charge, amount of charge in that section, mu times C, electric field. But this time, this mu is not a constant. This mu will be a field-dependent quantity, just as we saw in the last slide. Since this will not be a constant anymore, it will depend, the mu will depend on the local electric field, and that local electric field is varying at every point, right? Therefore, this time, when we sum them all up, we will be able to pick out the Ji, the current, because that current is continuous. Without recombination, current from one section to next is same. However, the mu, this time we cannot pick it up outside the sum, because at every section, the mobility depends on the local electric field. This is the only difference, nothing else. This is done. So that is the only difference that will give us the right answer. So again, all you have to do is to insert this value of Qi at each section. So let's do that. You remember that the Qi is, in the simplified bulk charge theory, we have Cox Vg minus Vt minus Mv, right? M is the body coefficient, do you remember? That's the effect of the drain voltage coming in the charge. That's why the charge goes smaller as you go from source to drain, right? That's minus Mv factor. Now you can integrate the right hand side. I will not even worry about it. But do you see on the left hand side what I have done for the mobility? The mobility is no longer just mu naught, because in that case it would be linearly proportional to the electric field, the velocity. Rather, I have that 1 plus E divided by EC, that extra factor that was giving us the saturation, I have inserted in there. Now this looks like a horrible integral, but you see in 2 seconds it will work out. This is how. The right hand side, you get the integration, you get the conventional looking square law type expression on the right hand side, no problem. But do you see on the left hand side how this works? So the mu naught you pull out, no problem. JD you pull out, current is continuous, you pull it out. But then this is, if you flip the numerator of the mobility field characteristics over, then you see there will be a 1, that's fine. And instead of the electric field, you will write, what should you write? Electric field is dV dx or dV dy in this case, because y is along the channel direction. So you have dV dy, and you can see that EC, E sub C is sitting there. That's the saturation field. That's 10 kilovolt per centimeter approximately, right? Now you can do this integral, right? There's nothing in there, because the first term is with 1 you pull it out. If you pull it out, then the integration of dy, well, that gives you the channel length. The first term is the channel length. What about the second term? You can see the dy will go away and you are left with dv. And if you integrate over dv, then correspondingly, the only thing you have is you will pick up a JD over EC that you can pull out, and you will have a VD left. And that, once you take you can then divide out throughout, and you will see that you have exactly the same expression as before, except that little term VD over E sub C sitting there. Apart from that, this is exactly what we had in the square law. So apart from that, we shouldn't have to worry about anything else. But that, of course, has an important meaning. See what happens. If you have 1 volt and EC is how much? 10 to the power 4, right? So that has a dimension of a length. If that length turns out to be larger than the channel length, and that will happen if your voltage is high, right? If your voltage is high, then that might happen. And in that case, the LC will actually disappear. LC will disappear because the second term on the numerator is actually larger. And if LC disappears, what it says that you will not get more current by making the channel length smaller. You see? Because there is no LC over there anymore. It's a very strange thing. But do you realize why that might happen? The reason is that as you increase the voltage, the electric field is going up, right? Electric field going up, at some point, the electrons cannot go any faster. So if you make your channel length smaller and therefore at every point the electric field goes up? Well, in that case, the velocity cannot go up, so therefore current remains constant, independent of voltage, right? So therefore you will see there is another consequence of that also. Because the velocity cannot go up, you will see the charge in Q3 and Q4, they also have flattened out. They are not going down. Remember in the original one, at each section the charge was going down? Look at this one. In the Q3 and Q4, we have higher than the saturation electric field. As a result, the velocity is constant. If velocity is constant, current is constant. Can the charge change? Of course not. So in that case, therefore, you will have a constant Q once the velocity saturation point has been reached. So this is very important. So therefore, you will not have a depletion in the velocity saturated regime. The charge will essentially plateau at one point and it will not go down any further. Again, how do you then calculate how the characteristics look like? You should take a derivative with respect to the drain voltage to see how the curve looks like and at what point they become maximum. So you have that IV characteristics, you just derived it. So we can take a derivative of this. Now the derivative is a little complicated because we have the numerator and the denominator all depending on the VD. So it takes a little bit, but the simplest is if you take log on both sides and then take the derivative, then it becomes very simple. And then you set the derivative to 0, and that gives you this horrendous looking expression, 2 Vg minus Vth divided by m, and you have the also a long denominator. This is something you should check out. It takes 5 minutes of algebra, but very, very simple. But first thing I want to point out here, do you realize that the point where this curve would saturate is a little less than where the square law curve, the simpler one that we derived in the last class and also in the beginning, little less than that. Do you realize? Because look at this. If I had channel length equal infinity, then the numerator of that curve, that has that mu naught, Vg minus Vth and all those things. If my channel length was infinity, then the second term on the denominator in the middle expression, that would have gone to 0. Then I would have 1 plus square root of 1. That's 2. Then 2 cancels the 2 on the numerator. That would have been equal to Vg minus Vth divided by m. Therefore, anytime I have finite L, definitely the denominator would be larger than the previous case, then 2. As a result, the overall expression Vd sat will be little lower. And that what simply says that the current will saturate at a little lower value compared to the square law. So again, you can do this. You can plot out these various quantities. But one thing you will notice now, look at this. This expression for ID doesn't have that square anymore. It is Vg minus Vt, but it doesn't have any square. And also, you do not have any mu left in this expression. You have simply Vsat, which is mu naught multiplied by E sub C, the saturation electric field. So this curve spaces out linearly. So therefore, if I give you an experimental curve, or if you are reading a journal paper and going through a particular paper, in 5 seconds, by just looking at the IV characteristics, you can immediately diagnose whether this is a short channel transistor or whether it's a long channel transistor. Because if these are going out linearly, then you immediately realize that this is a short channel transistor's velocity saturation is occurring, and immediately from the prefactor, you should be able to calculate the Vsat out from that expression, right? Because this is telling you that this is only will happen if the velocity saturation occurs. And you can take that expression, and assuming that Vd over EC is actually much larger than channel length, then you can essentially put those, I'm trying to evaluate the current at the maximum point, because beyond the maximum point, the current will be constant. And so therefore you put the VDSAT value in that we just calculated in the last slide, and that will give you the expression for the current VSAT, Cox, Vg minus Vth. Do you realize that this is a correct expression? Cox, Vg minus Vth is, what is that? That's charge, right? VSAT, velocity. Charge multiplied by velocity, that's current. So dimensionally it is correct. You will notice that there is a W missing between the top and the bottom expression. And the W is because in one case I have looking at ID, which is the total width dependent current, total current. And the top one is JD, is per unit width. So therefore you have a W difference. But other than that, exactly the same expression. And one way to show that how that current comes about is to, I think the real way to calculate the ID SAT, I just showed you an approximation, is to insert that entire VDSAT value in the ID expression. If you do the whole thing rather than the simpler expression I showed, then you will get a IV characteristics which looks very complicated. But the bottom line is that once you allow the L to be small, because we are talking about short channel, you will realize that how you get the final expression very easily. That goes as Vg minus Vth linearly rather than as a square. You should also try that if you let the L to go to infinity, this expression will go back to the square law. So therefore, both ends come out from this expression. So this is a few lines of algebra, but you should try it out when you're at home and see that it indeed works out. So let's look at some, how would you, just what I was mentioning a few seconds ago, that how one would know that you are in a velocity saturated regime, that if you look at IV characteristics, if it goes as a square of the Vg minus Vth, that will tell you you are in the long channel regime. And although I'm old, but I haven't seen any, and I have worked many years in industry, I haven't really seen any square law dependence in any transistor in last 20 years. So this is something historical remnant of how the transistors used to be, but all transistors now essentially will be either linear or slightly superlinear on this. So most of the time it's not Vg minus Vth per se, but raised to the power alpha, and the alpha is on the order of 1.1 to 1.3, something like that, but not definitely 2, not Vg minus Vt square, but not exactly linear either, but it's somewhere in between, but a close to 1, then close to 2. So this distinction is extremely important. That tells you about transistor characteristics. Now, many times in various exams, I set up a problem like this. I take something from a journal and put it there and ask you to calculate, for example, from here, I give you, let's say the y-axis is given, drain current is given. So I ask you, calculate the oxide thickness. Now, in many times, you should be able to do that, because you can see that from this expression, if W is given, you know VSAT, right? For silicon, 10 to the power 4 centimeter per second, volt per centimeter. Yes, or not, centimeter per second, velocity. And the field is volts per centimeter, 10 to the power 4 volts per centimeter. In that case, you know that, you know from here the Vg minus Vth, you can calculate Cox. And as soon as you know Cox, the oxide capacitance, you know the oxide thickness. So from a curve like this, you can pull out a whole set of full set of parameters associated with that transistor, with that process. So you should think about how to apply the transistor, how to apply this expression, not just how to derive the expressions. And as I said, that in practice, this Vg minus Vt, the alpha is obviously between 1 and 2, but close to 1 these days, not close to 2. Okay. So this is all I needed to say about classical transistors. Let me make a few comments about the bulk charge theory. Remember, we are talking about simplified bulk charge theory. The whole bulk charge theory looked horrendous, very complicated. I still want you to, you to understand this a little bit, but this is not something I would really place a lot of emphasis on, because this is not something that is used widely anymore. Now, you remember that when we looked at the inversion charge, then we had this Cox Vg minus Vth minus V, that was the first term, and then the whole bulk charge proportional to the accepted density. Now, the second term on the first line, that is because of the difference in depletion. Close to the source, you have one depletion. Close to the drain end, you have a different depletion. Therefore, that depletion, bulk charge depletion, is reflected in the second term of the equation. And you realize that this 2 phi sub b plus v, that type of expression, the depletion width goes as square root of v. Do you remember vbi minus va? That used to give us the junction width. So very similar to that. Now we actually took care of the second and in the second line, the last two items, we essentially didn't really handle this properly. We just made an equivalent and push it as an m multiplying the v. That was the simplified bulk charge theory. But if you wanted to keep the whole thing, it's no rocket science, because you can see how to handle this. So this was the square law. This was the simplified bulk charge. So we could handle that, no problem. Very simple integral. But the original integral is not impossible either. You can see it works very easily. All you had to do was do the same sum as before. Sum them all up, segment the channel into n number of sections. At every point, you sum up the current, and you do this integral on the second square root of 2 phi sub b plus v. That integral you do, that's not complicated. And at the end, what you get, because from the second integral coming from the blue, instead of m, what you get is a more complicated expression, but square root of v. You see, when you integrate, of course, you will have v to the power 3 halves divided by 3 halves. So that's what you have here, and that's why they call it 3 halves law for this, because this Vd comes as 3 halves. So this is essentially very similar to the bulk charge, simplified bulk charge theory that we talked about, but this in many textbooks, this is shown. Do you realize the second term in blue, or the terms in blue, that came as m multiplying Vd squared divided by 2. In the other case, that was m Vd squared divided by 2. So this whole thing, actually, only thing it does, it explicitly tells you how the doping dependence, Na, the accepted doping dependence, how it influences the current. Other than that, this doesn't have any explicit or much more insight than this. So you should be able to take a look and see how it works. Now, one thing I want to point out that, so everything I told you so far are fine, generally fine. But in transistors, lots of much more complicated things happen. For example, here what I'm showing you, that let's say you have a field-free region up to, let's say, 0.4 or so micron. This is an idealized case. Then a high field region. The field essentially goes up all of a sudden. And then again, the field comes down, let's say 1.1 micron or so, the field comes down and becomes small. So a low field, very high field, and a low field region. Now here you will see something strange happens, because we always thought that velocity is given by mu times the electric field. Therefore, in the beginning, the electric field should have been, the velocity should have been low. And let's say, and then when the electric field is high, the velocity should have jumped up in proportion. And then the velocity should have again gone down. Look at this, what actually happens. The rate curve says that it not only jumps up, it jumps up by 60%, much higher than the saturation value. That is called overshoot, velocity overshoot. The velocity versus field characteristics that I showed you before, remember that the thing saturating? That was actually for bulk semiconductors. You take a big chunk of silicon, put a uniform electric field and measure the velocity. Then change the battery or increase the voltage, measure the voltage again. That's for a bulk semiconductor. When in a small transistor, the electric field changes very quickly, then it is like, if you are driving a car, if you all on a sudden push on the accelerator, it doesn't immediately go to the saturation velocity. It may overshoot and then it may come down, right? With the friction, it may come down to the final value. And this overshoot many times are very important. That was not captured in our IV characteristics, right? So that is something, you see, it will come down to saturation velocity because the electric field is 10 to the power 5 volts per centimeter, which is higher than the critical field. So therefore, you can see that it has come down to 10 to the power 7 centimeter per second. However, in between, it has had a huge velocity overshoot. Therefore, the IV characteristics that we develop is reasonably okay, but doesn't really account for these overshoots and other non-equilibrium effects, and as a result, must be modified. Then that you will learn how to handle this in more advanced courses. And the main point I wanted to make, the velocity is not given by simply the bulk velocity field characteristics. It's a very important consideration. Another thing is that something is important to see. This is a MOSFET. You can see the source side, the N, and the drain side also, and then going between source and drain through the channel region. And you can see these black dots are the electrons. This is called a Monte Carlo simulation. A Monte Carlo simulation is where you take a random number and generate an electron with a particular energy and a velocity, and then let the electron go. And the electrons are scattered by the lattice, by phonons and various impurities, and it goes back and forth. And finally, it gets out either through the drain or through the source. Now, had it been a long channel transistor, like a couple of micron long, then you'd see all the black dots sort of hugging close to the conduction band because they have lost energy and they would have been very close to the conduction band. But these days, the transistors are so small that they get over that barrier, and many times they do not have enough time to scatter before they get out of the drain side. Therefore, all the things that we talked about, mobility, everything sitting in the bottom of the conduction band, effective masses, all those will not be correct anymore because these electrons are much higher in energy. So what I'm trying to tell you is that simplified laws that we learned is fine. But if you want to apply it to very small modern transistors like the Pentiums these days, then you have to be careful and do a more sophisticated calculations like this. You can also see that the velocity, look at the velocity of this particular transistor. Look at 10 to the power 7. That's supposed to be the maximum velocity. You are not supposed to go over it, right? That's the saturation velocity. But look that this is getting to close to 3 times 10 to the 7 because of all this non-equilibrium effect, because they didn't scatter enough. They simply essentially were going from the source to drain without too much scattering. So these are very important consideration and has been important consideration for a long time. So let me summarize then. One thing I wanted to emphasize today in today's lecture was the importance of velocity saturation, because if you have strong electric field, at some point the electrons cannot go any faster. Therefore, the charge must remain constant in order to keep the current constant, and therefore that is reflected by a linear dependence with Vg minus Vt that I have explained. Now, the bulk charge theory, which is encapsulated by the number m, the body coefficient, or in the full bulk charge theory that had the 3 halves that we derived, that actually explains why doping dependence of the body or doping of the body is so important in controlling the current. That Na, the accepted doping, why it's so important. And as I mentioned, that the velocity overshoot or the non-equilibrium effect in very short channel transistors, these actually complicate things very much. So therefore, if you take a job today in any of the companies, you will see that what I have told you so far about IV characteristics gives you the basics. But if you try to make a simulation just based on this and try to make an estimate, you will see that that does not immediately go with the experiment. But the thing is, it's still important to make simple estimate, because you wouldn't know otherwise whether a technician, let's say when you become a big scientist in a company, getting, let's say, paid a lot of money, then most of the time that you request a technician or a colleague to make some measurements, and they bring you some measurements, and you are not yourself doing the measurements. So how do you know that at that particular day a knob was not set properly? Or he may have made a mistake when he was reading off the data, or multiplied, Excel sheet multiply by the wrong constant. So the people who do not have simplified understanding about what the result should be, in the simple case, what the result should be, make an estimate, most of the time they are not very good engineers, because most of the time they cannot see what is normal and what is really abnormal, right? So therefore, although the simple things looks almost obvious, you will find it enormously useful when you actually, if you practice in industry. And also the same from universities. When a student comes back with some measurements, how do you know what he did in the morning? And the only way to check is to know in the back of your head this simple expression so that you can immediately check. Now for very short channel transistors, I told you very complicated theories, but in very short channel transistors, it turns out most of the electrons go from source to drain almost ballistic, meaning that without any scattering. And there is, Professor Mark Lundstrom, and in the industry, one of the most widely used theory for MOSFET about how current goes in very short transistors. He goes by his almost by his name, and this is a Lundstrom theory of MOSFET that encapsulates the ballistic transport. That's considerably simpler. When you make things very small, electrons don't scatter, then the expressions become considerably simpler. That we will learn in another course. Okay. Now, this is essentially the lecture I prepared for this saturation characteristics and others. I want to show you a few more slides, because in the last lecture, after I walked out and after I got a few emails from you, I realized that I have not been able to explain some things as clearly as I should have. So I want to take a moment and explain to you something that will be helpful to you. And this is about this charge getting smaller down the channel. And let me try to do it one more time, see whether it helps. So the point I wanted to make was that in the last lecture, I told you about that when you apply a drain bias, here for example, VR, that's the drain, the channel is this hashed region, and that's the depleted, the black part is the depletion region. The drain is N+, and so most of the depletion goes in the P region, which is lower dope. So I told you about that, and we explained that if we increase VR, then gradually there's this voltage potential drop as you go through the channel. And then I also explained that in order to invert this channel, instead of 2 phi sub B being sufficient, you will have to use this additional VR. Phi sub S must be 2 phi sub B plus VR in order to invert the channel. And it looks like to some of you or to many of you may not be, this might not have been as clear as I'd like. And similarly for this one, so essentially the same point. I want to explain the essence of this slide one more time, and let's see whether we can do that. And also where that bulk charge term comes from. So let's think about it. The point I want to make, you actually know this. You may not have realized this, but you actually know these expressions quite well. So let's start. Assume that you have a bulk piece of semiconductor. Red is the conduction band, blue valence band, and the dotted lines are electron and hole quasi-Fermi levels in equilibrium. If it is in equilibrium, then the Fermi level is close to the valence band. So here, you have a huge number of holes. That's the P. And you have a small, tiny amount of electrons. That's the red. How many electrons? Ni squared divided by Na. That's how many electrons you have. Tiny amount of electrons. Now, and you know that expressions for N and P. You already know that. that in terms of EC minus FM and EV minus FP. So you know that. Now, let's assume that I have applied a voltage in the gate, let's say, whereby I have pulled down the conduction band and the valence band without touching the Fermi level. Because Fermi levels are sort of independently set by the body contact and the drain contacts. So I have just pulled it down. What will happen to my electron and hole concentration? You know the answer. My hole concentration will become smaller. Do you realize? Because the Fermi level is farther out compared to the valence band. My electron concentration will be much larger than before because the Fermi level is now close to the conduction band. Is it already in inversion? Yes, this is already in inversion because I have a huge number of electrons compared to the hole. So things have gotten into inversion. Now let's say somehow, and I'm not telling you how, let's say somehow the Fermi level for the electrons, which is the red line, red dotted line, somehow I have pushed it down compared to where the Fermi level for holes are, the blue dotted line. What will happen? You know what will happen. This is what's going to happen. You see, the hole concentration I have not changed because the difference between hole Fermi level and the valence band remains the same. So that has not changed. But look at what has happened to electrons. Now electrons, because I have moved the electron Fermi level down. How? I'm explaining in a second. Because we have moved it down, so now the gap is larger. If the gap is larger, electron concentration will now go smaller, right? This is farther out. Now, instead of just having two parallel separation, if I instead have a step, how do I made this? I'll explain in a second. But if I made a step for the electron Fermi level, the red ones, then what would have happened? This is what would have happened. Because look, the blue Fermi level and the valence band, they are same separation, so I have the same hole concentration. But because the electron Fermi level is moving in a stepwise fashion, therefore the difference from this conduction band is changing. Further out it is more, so therefore you have less number of electrons down the channel, right? This part should be clear. Okay. Now, how do I do that? How do I make something step-like like this? And you already know the answer because you already have done a homework like this. And that was the purpose of that homework. Do you remember that if I have a PN junction and then on the N side, if I apply a voltage, then the voltage, the Fermi levels remain flat up to the other side of the junction, and then gradually it goes back to the main region, right? Do you remember that? So that is exactly how that step comes about. Because this is essentially the PN junction that you have done when you had the recombination problem. Remember, when you did the recombination problem, you had this reverse bias PN junction and you had to calculate the recombination at various points. This was exactly that expression. And this then is the charge that you see in those expressions. You see that along the channel, you have the charges actually starting from the source end to the drain end. The charge is gradually going down. This is the same reason the charges go down in the normal PN junction, because as soon as you apply a drain bias, the whole thing is reverse biased. And that splits the Fermi level and makes the electron Fermi level lower than the whole Fermi level, right? And then it will eventually come back and come together. And that's being reflected in these steps in the charges. Okay? And so that's all I wanted to emphasize to you, because this variation in the charge looks complicated, but this is something you have seen before and you should be able to easily understand it without too much effort. Now what will happen regarding the depletion? You know, there's a second piece. Now in depletion, what happens? Let's say that's the accepted density, the green. You apply a gate bias as we have done before. Electron concentration goes up, but this time I'm just plotting the depletion charge, the Na, And so at some point it will invert. The channel will invert at some point. Now, however, if your electron Fermi level is actually have been pushed down, then do you realize that your electron concentration must be going down, because the separation between conduction band and the Fermi level is now more than before. So electron is less. Now, if you want it to invert, then what do you have to do? You'll have to put more gate bias here, right? More gate bias, so that you, again, it's like trying to chase the Fermi level. First time it came close to the Fermi level, it got a certain amount of charge. Now it has a moving target. The Fermi level has been pushed down. So now you'll have to, if you want to again invert it, you will have to push it down even more, so that the separation again becomes the same as before. Then again it will invert. In order to do that, then therefore you'll have to apply more gate bias, and that gate bias therefore will result in more depletion, right? So therefore, when you move the Fermi level like this with a drain bias, then the depletion width also keeps changing. Okay. So I'll end here. Let me end here, and hopefully we'll go back in the previous lecture and read it along with this particular material, or try to understand it in this material, so that everything becomes clear. Okay, thank you.